This is Vulcan Mission Control at T-minus 7 minutes and holding. Building rockets requires a large team, more than just the ULA team. At ULA, we have a team of over 45 suppliers that span 22 states. 20 suppliers in addition to our Colorado and Virginia sites as well. This is Vulcan Mission Control at T-minus 7 minutes and holding. The Vulcan Centaur rocket was developed with a low-risk path to first flight. 90% of the capabilities and designs of the Vulcan rocket will be flown before the actual first flight. The program was developed by leveraging our heritage vehicles, Atlas and Delta, and using some of those technologies to give us this heritage experience and flight heritage as we lead to the initial ILC. So as you can see, some of the items like the payload fairing, the pressure stabilized stainless steel tanks, and structurally stable aluminum tanks go all the way back to our heritage vehicles. In addition, we've on-ramped some capabilities over several cut-ins of the Atlas and Delta vehicles to get us some flight heritage here over the last several years. Some of those capabilities included updating our payload fairing manufacturing process and modifications, now flying dual RL-10 engines, updates to our common avionics system and software, and then most recently implementing new SRBs that have flown first on the Atlas vehicle. So ultimately, here at our first flight, we have several flights across all of these components, and the BE-4 engines are truly the first flight component on the Vulcan vehicle. This is Vulcan Mission Control at T-minus 7 minutes and holding. ULA's Atlas rockets have launched many of the world's vital space assets. Let's take a look at the impressive legacy of the Atlas family of rockets, which has significantly contributed to the development of Vulcan Centaur.
And the RD-180 engine roars to life and liftoff of the maiden flight of the Atlas V rocket with a Hotbird 6 spacecraft on board.
As the inaugural flight of the Atlas V lifted off on August 21, 2002, it carried with it the dreams and aspirations of thousands of rocket pioneers who had laid the foundation that made it possible. Atlas V continues the Atlas legacy of innovation and accomplishment that has been vital to our nation for more than half a century. Named after the mighty giant of Greek mythology who carried the world on his shoulders, Atlas was conceived as a weapon and a deterrent, but evolved into a system that pushed the envelope with trailblazing innovation and steadfast reliability. At the request of the Air Force, Charlie Bossert and his San Diego-based engineering team began work on a demanding set of requirements to design an intercontinental ballistic missile capable of delivering a 1,500-pound warhead to a target 5,500 miles away. Their answer, which became known as Atlas, was the top national priority in 1955 as the race with the Soviets engulfed the country. On June 11, 1957, the first Atlas flight lifted off from Space Launch Complex 14 at Cape Canaveral, Florida. The flight ended 38 seconds later, but Bossert's team had taken the first step and proven the structural integrity of their innovative pressure-stabilized steel tank. Complete success for the Air Force and Bossert's team would come just 5 months later, on December 17, 1957.
Go, honey, keep going, baby.
Though the Soviets had beaten the U.S. to space with the launch of Sputnik in October 1957, President Eisenhower would counter a year later when Atlas 10B delivered his holiday message of peace from orbit 180 miles above Earth. Known as Project SCORE, the orbiting Atlas booster became the world's first communication satellite.
This is the President of the United States speaking. Through the marvels of scientific advance, my voice is coming to you from a satellite circling in outer space.
Attention all personnel, report to the blockhouse immediately. Countdown will begin.
On September 9, 1959, Atlas 12D became America's first operational ICBM, following launch from California's Vandenberg Air Force Base. In all, 350 Atlas ICBMs were built and stood on operational alert through 1965. The surplus boosters were refurbished and used by the Air Force, the Army, the Navy, and NASA. The last refurbished booster was launched in 1995. By the early 1960s, the Atlas booster had made the transition from missile to space launch vehicle, and 1962 proved to be a pivotal year. Riding atop an Atlas booster in Project Mercury's Friendship 7 capsule, John Glenn became the first American to orbit the Earth on February 20, 1962. Three additional Mercury flights, carrying astronauts Scott Carpenter, Wally Schirra, and Gordon Cooper, set the stage for the Gemini flights and the Apollo missions to the moon. Later that year, Atlas scored another first when Atlas 179D, equipped with an Agena upper stage, lifted off from Space Launch Complex 12 at Cape Canaveral. Its payload, NASA's Mariner 2, became the first successful interplanetary spacecraft. 1962 also marked the debut of the Centaur upper stage, the first to harness the power of liquid hydrogen. The Centaur upper stage, to this day, remains a hallmark of the Atlas system. Together, with its Agena and Centaur upper stages, the Atlas booster went on to play a significant role in America's exploration of the solar system, launching virtually every exploration mission in the 1960s and 1970s.
It was the first spacecraft that was launched from Earth that had enough energy to escape the entire solar system.
During the late 1970s and 1980s, Atlas continued to play important roles in the development of our nation's space program. In addition to building our national security presence in space, converted Atlas boosters also launched the Air Force's Navstar demonstration satellites, leading to the navigation system known today as GPS. In the late 1980s, General Dynamics saw an opportunity to bring commercial payloads back to expendable launch vehicles, and on July 25, 1990, AC-69, the first Atlas I, ushered in a new commercial era for Atlas. The commercial era brought 8 new Atlas configurations over a 14-year span, each carrying an operational payload. The commercial program has enabled breakthroughs in communications, meteorology, broadcast technology, navigation, and national security. In 1995, development of the Atlas III vehicle began. In a bold move, the Atlas booster engine system was replaced with the powerful RD-180, which generates 860,000 pounds of thrust and has throttle capability resulting in a smoother and more efficient ride. Making its debut from Space Launch Complex 36 on May 24, 2000, the Atlas III provided a substantial performance improvement over the Atlas IIAS. Reliability was increased by reducing the number of engines from 8 to 2 and the elimination of 5 staging events, as well as more than 10,000 parts.
This is Atlas Mission Control at T-minus.
In 1998, the Atlas team embarked on a development project for the United States Air Force that would forever change the Atlas vehicle.
And the RD-180 engine roars to life and liftoff with a maiden flight of the Lockheed Martin Atlas V rocket with a Hotbird 6 spacecraft on board for Eutelsat in Paris, France.
For more than 40 years, Atlas vehicles had relied on the pressure-stabilized steel tank developed by Charlie Bossert and his team. In a departure from conventional thinking, the Atlas V development replaced the tank with a structurally stable common core booster. In addition to vehicle modifications, the team took a new approach to processing and launch. Atlas V processing is done vertically, and the mobile service tower has been replaced by a mobile launch platform, which carries the entire assembled vehicle to the launch pad, ready to fuel and launch. The Atlas V is expanded to multiple payload fairing and solid rocket booster configurations, as well as re-establishing a launch capability from the West Coast at Vandenberg Air Force Base. The Atlas vehicle has a long legacy of accomplishment. This record of success, which is nearly unparalleled in the launch industry, is built on the lessons handed down from more than 60 years of Atlas experience. It is also a credit to the dedication and persistence of the Atlas team and their passion for mission success, one launch at a time.
This is Vulcan Mission Control at T-minus 7 minutes and holding. ULA's Delta IV Heavy is the nation's proven heavy lifter. Let's take a look at the evolution of this impressive rocket.
Though first launched in 1960, Delta's story really begins in the mid-1950s with the development of the Thor Intermediate Range Ballistic Missile. Named after the Norse god of thunder, Thor was created in response to a growing fear that the Soviet Union would beat the US in the deployment of a long-range ballistic missile. The goal was to design a system that could deliver a nuclear warhead to a target 2,300 miles away, the distance between the United Kingdom and Moscow. On January 25, 1957, the first Thor lifted off from the newly constructed Space Launch Complex 17 at Cape Canaveral. Following a series of early failures, the Thor team celebrated their first success on September 20, 1957. In all, 59 Thor IRBMs were launched, with the last flight occurring in 1975. Thor began the transition from missile to space launch vehicle in 1958. On October 11, 1958, America's newly formed space agency marked its inaugural launch when Thor Able boosted NASA's Pioneer 1 on a mission to the moon, and NASA's long partnership with Thor was born. NASA and the Douglas Aircraft Company began development of the fourth and longest-lasting Thor configuration in April 1959. Using a Thor first stage and a Vanguard second and third stage, Delta I lifted off on May 13, 1960 from Cape Canaveral Space Launch Complex 17. Though its first launch was not successful, the Delta team quickly pinpointed the failure and 3 months later delivered NASA's Echo 1 communications satellite to orbit. Following Echo 1, the Delta team racked up an impressive 22 successful launches. Led by Bill Schindler, the Delta rocket earned its industry workhorse moniker for rapidly establishing itself as one of the most reliable and versatile launchers. During the 1960s, Delta launch vehicles paved the way for the burgeoning communications industry, launched America's first weather satellites, and sent probes to explore our universe. AT&T's Telstar 1, the first commercial communications satellite, launched in 1962, and in 1963, SYNCOM-2 became the world's first geosynchronous satellite. TIROS, or Television Infrared Observation Satellites, provided the National Weather Service with humans' first view of the Earth's cloud cover. In orbit around the Earth, Moon, and Sun, NASA's Explorer satellites provided us with a deeper understanding of the solar wind, cosmic rays, as well as Earth's magnetic field and radiation belts. By the end of the decade, launch vehicle modifications, including the addition of solid rocket motors and an upgraded third stage, made it possible for Delta to orbit satellites 10 times larger. The 1970s was an international decade for Delta, as the manifest included scientific and communication satellites for several countries across North America, Europe, and Asia. Perhaps the most demanding challenge of the 1970s was the launch of the Earth-imaging Earth Resources Technology Satellite, later known as Landsat. The mission for the Earth sciences community required major changes to the Delta propulsion and guidance systems. During the 1980s, Delta continued its reliable service to the communications, weather, and Earth imaging communities. As capable as the Delta rocket proved to be, production came to a halt in the early 80s when national space policy dictated that the space shuttle be used as the U.S.'s primary launcher, signaling the end of the expendable launch vehicle. But in 1987, the Delta team picked up where they left off, and development began on a launch vehicle to support the Air Force's Global Positioning System. On February 14, 1989, Delta 184 began a new chapter in space launch history as it lifted off from Space Launch Complex 17, demonstrating an incredible feat. The Delta II had gone from development to launch in just 2 years. To accommodate the larger GPS satellites, engineers improved the Delta rocket in several ways. The fuel tanks were stretched, a new payload fairing was developed, and larger solid rocket motors were incorporated. The modifications resulted in increased performance and flexibility. By the mid-1990s, the Delta II had delivered the fully operational 24-satellite GPS constellation. And though it was developed for the Air Force, Delta again became a reliable partner to both NASA and its commercial customers. Over the course of its more than 20-year run, the Delta II has launched some of America's best-known scientific and exploration missions.
Plus 4, 3, 2, we have main engine start, 0, and liftoff of the Stardust spacecraft. Liftoff of the Delta II rocket carrying the Spirit from Earth to planet Mars.
Liftoff of the Delta II with Grail. Journey to the center of the moon.
On the commercial side, Delta II launched the Global Star and Iridium constellations, which brought satellite telephone communication to the world. Continuing its evolution to meet the growing demands of its satellite customers, the Delta team developed the more powerful Delta III. Though short-lived, the Delta III doubled the performance of the Delta II.
Ignition and liftoff of the Boeing Delta III rocket.
Stage systems looking normal. Engine burners keep burning normally, and all 6 ground.
In partnership with the Air Force's evolved Expendable Launch Vehicle program, the Delta team began development of the next generation Delta rocket in the mid-1990s.
And we have liftoff of the first Boeing Delta IV rocket carrying the W5 telecommunications satellite for Eutelsat of France.
All Delta IV configurations begin with the Common Booster Core, powered by the RS-68A main engine. The Delta IV Heavy, with its 3 Common Booster Cores, deliver our nation's largest missions to orbit.
Liftoff of the United Launch Alliance Delta IV Heavy rocket carrying the NROL-32 mission for the National Reconnaissance Office.
Delta IV launch vehicles are produced at a 1.5 million square foot state-of-the-art facility in Decatur, Alabama. Processing and launch takes place at Space Launch Complex 37 at Cape Canaveral Air Force Station and Space Launch Complex 6 at Vandenberg Air Force Base in California.
Range safety arm light on. Right. Affirmative. Range ready. Ready. Water system ready.
From its early beginnings as a weapon and deterrent, through its transformation into a space launch vehicle, Delta has reliably supported our nation for more than 60 years. Delta's legacy as a workhorse continues today and is a testament to the persistence, dedication, and commitment of an enterprising team that has continually evolved the Delta rocket to support a changing world.
5, 4, 3, 2, 1, and liftoff of the United Launch Alliance Delta IV Heavy rocket.
This is Vulcan Mission Control at T-minus 7 minutes and holding. ULA also launches Atlas and Delta rockets here in Cape Canaveral, Florida. Let's take a look around.
With missions launched to every planet in the solar system, as well as critical national security, science, weather, and communication satellites, ULA has established a long-standing reputation for reliability and orbit accuracy in the space launch industry. At our launch site in Cape Canaveral, Florida, the story begins with ULA's Atlas and Delta rockets arriving on the RS rocket ship. The rocket ship is a specially designed cargo ship used to transport rockets from ULA's 1.6 million square foot production facility in Decatur, Alabama. Rocket ship is large enough to carry a complete Delta IV Heavy rocket. That's 3 boosters, a second stage, and a payload fairing. Once loaded, rocket ship departs ULA's dock and travels through the Tennessee River, then onto the Ohio and Mississippi rivers, then goes out into the Gulf of Mexico. From there, the ship travels through the Atlantic Ocean, around the southern tip of Florida, and north to Port Canaveral. Rocket ship was designed with several features to ensure successful delivery, including the ability to adjust its draft for shallow water and rudderless steering, which minimizes the need to tug. Atlas V boosters are transported from the ship to the high bay in the Atlas Spaceflight Operations Center, or ASOC, for final preparations. Delta IV boosters are moved to the Horizontal Integration Facility, or HIF, where they are mated together to form the Delta IV Heavy configuration. With final checks completed, the boosters are transported to the launch pad for Launch Vehicle on Stand, or LVOS. The 107-foot-long Atlas V boosters are brought to Space Launch Complex 41 and are hoisted into a vertical position using a crane and placed onto the Mobile Launch Platform, or MLP, in the Vertical Integration Facility, or VIF. Delta IV Heavy rockets are raised vertically by a fixed pad erector at Space Launch Complex 37. The fixed pad erector uses a single hydraulic piston to rotate the boosters 90 degrees inside the Mobile Service Tower, or MST. LVOS is followed by the addition of solid rocket boosters, and then the second stage. Next comes Wet Dress Rehearsal, or WDR, which is an end-to-end launch simulation, from fueling through spacecraft separation. Meanwhile, the ULA team is also working simultaneously to help the customer encapsulate their payload into the rocket's payload fairing. The encapsulated payload fairing is the final piece to be mated to the rocket. With the rocket stack complete, the spacecraft team tests all of the interfaces with the rocket and the launch pad. Once the rockets are completely assembled, final launch preps begin. For Atlas V rockets, launch countdown begins with moving the rocket from the VIF to the pad. The quarter-mile trip uses 6 components to complete the 20-minute trip. Weighing in at about 2 million pounds, the MLP supports the rocket and contains air conditioning, electrical, and commodities, while the undercarriages bear the weight of the MLP and rocket. 2 rail cars lead the move, with the payload van providing communication to the payload, while the ground van houses the ground support for the rocket. At the rear of the convoy, the portable environmental control system provides air conditioning to the payload and rocket. Finally, track mobiles provide the power to move the 3.5 million pound convoy. For Delta IV Heavy rockets, the process looks quite different. Approximately 9 hours before T0, final preparations begin as 40 hydraulic cylinders at pressures nearing 3,500 psi move the 10 million pound MST. It's first raised 8 inches and then rolled back. Delta uses a carriage transporter system, traveling at about a quarter mile per hour. It takes about 25 minutes to roll the MST to its launch position, 345 feet north of the Delta IV rocket. The Delta IV rocket stands 217 feet tall, or about 21 stories, and weighs more than 900,000 pounds fully fueled. On the day of launch, nearly 30 engineers and managers are polled for system status and readiness to proceed.
Status check to proceed with terminal count, Atlas Systems, propulsion.
This is the final status check before launch for all Atlas and Delta vehicle systems, ground systems, the spacecraft, and the U.S. Air Force Eastern Range. The vehicle system readiness poll includes electrical systems, hydraulics, pneumatics, propulsion systems, flight control, and propellants.
Range coordinator. Clear to proceed. Launch director.
Launch vehicle is ready to launch.
Mission director.
This is the mission director. You have permission to launch.
Proceeding with the count.
If the rocket is ready for flight and the weather is within the launch commit criteria, then polling will be completed and the team will have given the go for launch.
T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. There's ignition. And liftoff of the United Launch Alliance Atlas V rocket.
For a typical Atlas V flight, the main engine and solid rocket boosters ignite to lift the rocket off the pad. Shortly after liftoff, the rocket begins a pitchover to attain the proper flight path, minimizing the dynamic pressure the vehicle experiences during flight. Within the first few minutes of flight, the vehicle reaches Mach 1, the speed of sound, followed by jettison of the solid rocket boosters. About 4 minutes later, propellant levels deplete and the booster engine shuts down, followed by release of the booster stage. At various times in flight, depending on the mission, the vehicle jettisons its payload fairing. From there, the second stage will continue carrying the spacecraft towards its destination with planned engine starts and stops. Finally, Centaur will release the spacecraft in its target orbit to continue its journey.
This is Vulcan Mission Control at T-minus 7 minutes and holding. We just received confirmation from launch conductor Dylan Rice. Our new T0 is 9:05 p.m. Eastern Time. ULA builds Atlas, Delta, and Vulcan rockets in a 1.6 million square foot facility in Decatur, Alabama. Here's a look inside.
Successfully launching missions to every planet in the solar system, in addition to critical national security, science, weather, and communication satellites, ULA has established a long-standing industry reputation for reliability and orbit accuracy. While our rockets lift off from launch pads in Florida and California, the journey to space begins in Decatur, Alabama. At approximately 1.6 million square feet, ULA's production facility is an always-on workhorse where technicians simultaneously build components for Atlas V, Delta IV Heavy, and Vulcan Centaur rockets. Booster production begins when large aluminum plate stock is loaded into one of 4 double gantry skin milling machines, where aluminum is milled into patterns designed for building tanks and other components. This process helps reduce the original weight of each panel by 70%, while maintaining approximately 75% of the original material strength. After machining, skin panels are transported to the brake form and bump pressed into the precise curved radius required to create fuel tank barrel sections. Components made from aluminum require anodization to protect from corrosion. For this requirement, certain components, like skin panels, are first given a high-pressure wash and then dipped in a series of chemicals to complete the sealing process. Skin panels are then transported to the vertical friction stir welder, where they are lifted and forged together to form the barrel sections of the fuel and oxidizer tanks. Delta IV and Vulcan Centaur tanks are comprised of 5 skin panels, while 4 skin panels form the Atlas V tanks. Friction stir welding is a unique process accomplished by a pin tool, which applies frictional heat and stirring of the parent material to form a weld. This process only uses friction as the heat source and has no filler material, making an extremely strong welded joint. Completed aluminum barrel sections then move to the circumferential friction stir welder, where domes are welded to each end, completing the first stage fuel tanks. After pressure testing, which verifies the integrity of the welds, the next stop for booster fuel tanks is the spray-on foam insulation booth, or SOFI. This is where completed tanks are primed, then insulated to protect from the acoustics that occur at liftoff. Tanks then move to final assembly, where components like wiring and engines are added. In addition to the first stage, or booster stage, ULA's second stages are also built in Decatur. The factory has recently undergone a major reconfiguration, resulting in a new state-of-the-art Centaur V production line to increase the speed at which Vulcan Centaur second stages are built, assembled, and tested. The Centaur upper stages for Atlas and Vulcan are built using a thin stainless steel structure, making it the most efficient upper stage currently in use. To create the domes or bulkheads for Centaur's 2 tanks, gores, or pie-shaped sheets, are welded together. The bulkheads and tank skins are then assembled using a combination of spot and seam welds. Spray-on foam insulation, or SOFI, is then applied to the Centaur tank to provide thermal protection for the cryogenic fuels. Centaur's tanks are known as pressure-stabilized tanks because 90% of their weight and structure at launch is from the mass of the fuel and oxidizer loaded prior to liftoff. The Centaur tank then moves to final assembly, where engines, avionics, pneumatic, and propulsion systems are installed. At the end of the production journey, all systems on both the booster and Centaur are fully tested, and the stages are prepared for transport to the launch site. With testing and transport preparations completed, Atlas V, Delta IV Heavy, and Vulcan Centaur rockets exit the factory and roll about a mile down the road to a dock on the Tennessee River. Once loaded onto the RS rocket ship, ULA's specially designed cargo boat, the rockets begin the 8-day trip to Cape Canaveral Space Force Station, Florida. or the 23-day trip to Vandenberg Space Force Base, California.
As we talked earlier, we've made modifications to Slick 41 so that it can support both the Atlas and Vulcan launch systems, making it the only operational dual-use pad. As you can see here, this is the new launch platform that is specific to the Vulcan vehicle. Also at the pad, we've added additional fuel tanks, enabling the ability to supply liquid methane to the booster stage. We've also updated the acoustic water suppression system to protect the pad during engine firing. Vulcan was designed to be similar in height to the Atlas vehicle to enable many of the key interfaces between the vehicle and launch infrastructure to remain unchanged. This is Vulcan Mission Control at T-minus 7 minutes and holding. In a few minutes, launch conductor Dylan Rice will poll the team for the final go to pick up the count. While we wait, let's learn about today's flight readiness firing from ULA's President and CEO, Tori Bruno.
This is such an exciting day and one that we have worked so hard to reach. The first Vulcan flight rocket is on the launch pad. Flight Readiness Firing, or FRF as we like to call it, is a full vehicle tanking and engine hot fire for several seconds. The FRF includes tanking of the Vulcan booster and Centaur 5 tanks to assess pre-launch procedures, including a terminal count demonstration starting at T-minus 7 minutes and culminating in a short duration engine firing. Test takes place at Space Launch Complex 41 at Cape Canaveral, the only currently operational launch pad capable of launching 2 different rockets. Objectives for the PTT and FRF include systemic validation and testing of flight-configured launch vehicle and its associated ground support equipment, including demonstration of day of launch integrated closed-loop control of vehicle systems and the BE-4 engines. Confirmation of operational readiness of vehicle airborne and GSE systems, facilities, as well as ground and flight software. So truly an end-to-end preparation and practice for that big launch. Demonstration of successful vehicle command and engine start sequence and shutdown is also part of this, as well as validation of operational timelines and sequences. The test approach for PTT number 2/FRF allows us to buy down risk as we demonstrate the system in a measured manner. Such an exciting day. Go Vulcan, go Centaur, go FRF.
We remain in the planned hold as we continue towards FRF. 29 engineers and managers are polled for system status and readiness to proceed. This is the final status check for all Vulcan vehicle systems, ground systems, and the U.S. Space Force Eastern Range. The vehicle system readiness poll includes electrical systems, hydraulics, pneumatics, propulsion systems, flight control, and propellants. Let's listen in as Dylan Rice performs the final polling.
All steps complete prior to the status check. LC switch is ready. Status check to proceed with terminal count, Vulcan systems, propulsion. Go. Hydraulics. Go. Pneumatics.
Go. Go.
LNG. LO2. LO2.
Go.
Water.
Go.
Centaur systems, propulsion. Go. Pneumatics. Go. LO2.
Go.
LH2.
Go.
Has gas.
Go.
Electrical systems, airborne.
Go.
Ground.
Go.
Facility.
Go.
RFFDS.
Go.
Flight control.
Go.
CCQ.
Go.
Operations support.
Go.
COM.
Go.
Umbilicals.
Go.
ECS.
Go.
Red line monitor.
Go.
Quality.
Go.
Op safety manager.
Go.
ULA safety officer.
Go.
Vehicle system engineer.
Go.
Anomaly chief.
Go.
Range coordinator.
Clear to proceed.
Launch director.
Launch vehicle is ready for FRF.
Mission director.
You have permission to execute FRF.
Proceeding with the count. ALC, verify T0 is set for 0105 Zulu.
Verified.
Polling is complete. The ULA team is go for today's flight readiness firing. A few minutes before firing, you'll be listening to Dylan Rice and his team performing the final steps in the countdown procedure. Several critical activities occur in the final minutes, including verifying fuel tank and pressure levels in both the Vulcan booster and the Centaur upper stage. Within the final 15 seconds, you'll hear "Go FRF." This is the final status check of the Vulcan and Centaur readiness. At T-minus 7 seconds, the ROFIs, or radial outward firing igniters, ignite. At T-minus 5 seconds, start command is sent to the engines. At T-minus 3 seconds, the main engines ignite to demonstrate BE-4 operation in the integrated vehicle system. At T0, the BE-4 engines will throttle down, mimicking the nominal shutdown that typically occurs at booster engine shutdown, or BECO. Before we continue, let's check in on the weather this evening. Ground winds are 5 knots out of the south, and the temperature is 77 degrees Fahrenheit. There are no concerns for rules. This is Vulcan Mission Control at T-minus 7 minutes and holding. We anticipate releasing the hold in just a few moments.
3, 2, 1, mark. 655.
Ground pyros enabled.
The countdown clock has resumed, and we are go for flight readiness firing at 9:05 p.m. Eastern. A few minutes from T0, we'll raise the volume on our team so you can hear the final preps taking place. This is the first time the team will fire up the Vulcan rocket's BE-4 engines at Space Launch Complex 41. Let's learn more about this innovative rocket.
ULA's new Vulcan rocket is designed in Centennial, Colorado, and built in ULA's 1.6 million square foot production facility in Decatur, Alabama. At the base of the rocket is the Vulcan booster, comprised of 2 aluminum propellant tanks and powered by dual BE-4 engines. Atop the booster is the ULA Centaur second stage, powered by twin RL-10C-11A engines. The Vulcan booster with the Centaur stands more than 150 feet tall and is 5.4 meters in diameter. The newly completed Vulcan rocket traveled from Alabama to Cape Canaveral on ULA's rocket ship. Once in Florida, a series of events led to today's countdown. The process began by lifting the 109-foot booster onto the new Vulcan launch platform, or VLP. Then, the Centaur's second stage was transported to the pad and lifted into position. Countdown to the hot fire began when the rocket, on the VLP, was moved a third of a mile from the Vertical Integration Facility, or VIF, to the pad. Weighing in at approximately 2 million pounds, the VLP supports the rocket and contains air conditioning, electrical, and commodities lines. During the 20-minute trip, 3 rail cars lead the convoy, including the ground van, providing support for the rocket, the support van, providing power, as well as the Vulcan payload van, providing support to the payloads. At the rear of the convoy is an environmental control system, providing air conditioning to the rocket. Trackmobiles power the nearly 3 million-pound convoy. With the Vulcan rocket on the pad, the ULA team transitions to fueling and other preparations for this vital pre-launch test.
This is Vulcan Mission Control at T-minus 3 minutes 54 seconds. For today's test, we have support from our Launch Console operators and engineering teams at both the ASOC here at the Cape and in Colorado at our Denver Operations Support Center. While today's test is primarily about testing the vehicle and ground systems, it also serves as an opportunity to train and certify our launch team to support the first flight of the new Vulcan vehicle. This vehicle configuration is unique to the FRF test, with no spacecraft, payload fairing, or SRBs. After a successful FRF, the vehicle will be inspected and reconfigured into the flight article. It will then follow our standard processing operations, and the encapsulated spacecraft and SRBs will be mated before launch.
Two minutes, 38 seconds. 2 minutes, 30 seconds.
You may also notice that the Vulcan logo is covered in a layer of ice on both the booster, LOX, and methane tanks. These aluminum tanks are uninsulated, so condensation freezes when the tanks are filled with cryogenic propellants. The portions of the vehicle without ice are composite structures or are covered in SOFI, spray-on foam insulation.
Vehicle internal. Launch sequencer start. 1 minute, 50 seconds. One minute, 40 seconds. Launch enabled. 1 minute, 35 seconds. FTS armed.
T-minus 90 seconds. The rocket, ground systems, and eastern range are go.
1 minute, 20 seconds. SCS count started. $60 seconds.
We're about 1 minute away.
Vulcan tank set step 3.
$16.
Ground vent valves secured.
Go, FRF.
T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2. We have ignition.
LC switch not ready.
Ready to reset the clock to T-minus 7.
LC, reset the clock, countdown clock to
We
T-minus 7
just saw
minutes and holding.
ULA's Vulcan engines throttle up for the first time.
LC, this is Peony 1.
Go, Peony 1.
Vulcan tank pressures are stable.
Rice announce ignition, power, and shutdown of Vulcan's twin BE-4 engines. The team is now looking at how the engine operated, analyzing data from the firing, and safing the vehicle as we prepare to detank.
Go ahead.
I'm looking for a status at step 40.
Max in chill mode.
Roger.
And LC, this flight control.
Go.
Step 60 SBAPS. SS.
Once we start detanking and the booster tanks start to warm up, the Vulcan logo will reveal itself again. The rocket you see at Slick 41 today is the same vehicle that will be launching the first certification flight. Let's learn more about how it's built.
Vulcan Centaur production begins with aluminum sheets expertly machined to remove more than 2/3 of the weight, resulting in the structurally strong yet lightweight orthogrid panels that form Vulcan's propellant tanks. The panels are then bump pressed to form the curves required to complete the tanks. At the same time, rings, adapters, and other structural components are precision milled. Next, the aluminum domes, panels, and other structures that form Vulcan's propellant tanks are first cleaned and etched to a smooth, even surface, and then anodized to harden and prevent corrosion. Following an ultrasonic inspection, 5 completed panels for the liquid methane tank are assembled and joined together using friction stir welding. Unlike traditional welding, where filler material is used to join components, friction stir welding uses a head to stir the metal of the 2 panels together as it moves down the seam. The resulting joint is stronger and produces a lighter weight, higher performing tank. The process is repeated to create the liquid oxygen, or LOX tank, followed by attaching domes to complete the tanks. Circumferential friction stir welding is then used to join the 2 propellant tanks that comprise the Vulcan booster. As production continues on the booster stage, stretch-forming gore panels for the Centaur's second stage propellant tanks is underway. The stainless steel gore panels are welded together to create the propellant tank domes. The gore welder is one of several highly specialized welding stations in the Centaur production process. Just down the aisle, Centaur 5's massive intermediate bulkhead is mated to its ultra-thin tank. Once both propellant tanks are welded, they're mated together to create the Centaur 5 second stage. Before moving to final assembly, the 5.4-meter booster welds are sprayed with foam insulation, followed by booster mask and paint. Twin BE-4 engines are individually hot-fired prior to making their way to the factory. They are then mated to Vulcan's thrust structure and protected by a heat shield. With production complete, Vulcan's first and second stages depart the Decatur factory and make their way to ULA's rocket ship to begin their journey to the launch site. Meanwhile, at Cape Canaveral's Space Launch Complex 41, modifications have been made to the launch pad to accommodate the Vulcan rocket. The water suppression system has been upgraded and tested, along with other updates, including new, larger fuel storage tanks. Additionally, in the Vertical Integration Facility, or VIF, platforms have been modified to accommodate this larger vehicle. Following the journey to Cape Canaveral, the Vulcan components are offloaded from rocket ship and transported to the VIF, where they are lifted onto the newly constructed Vulcan Launch Platform, or VLP. The vehicle then travels 1/3 of a mile to the pad to fill both propellant tanks, followed by flight readiness firing of the booster stage.
This is a huge accomplishment. In just a moment, I'll have the opportunity to speak with ULA's Vice President of Vulcan Development, Mark Peller. Before he joins us, let's take another look at the exciting final moments of the count through firing of Vulcan Centaur.
16.
Ground vent valves secured.
Go, FRF.
T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, we have ignition.
LC switch not ready. Countdown clock to
We just saw ULA's Vulcan engines throttle up for the first time. Hi, Mark. Thank you so much for joining us. We've just watched the flight readiness firing of the Vulcan vehicle. Congratulations. How are you feeling?
Thank you, Amanda. Well, a whole range of emotions, obviously. Super excited, relieved, I'll be honest, and just very gratifying. A lot of hard work by the whole team, many, many years of work to get us to where we are here today.
Absolutely, and this was a really big milestone on our path to first flight. Can you talk a little bit more about what this test was and what the objectives for today included?
Sure, this is a huge milestone. This is as close as you can come to launching a rocket without actually launching the rocket. So complete integrated test of all the airborne elements, the ground systems, all coming together, putting it through everything that we would on a normal day of launch, obviously up to including actually starting the main engines, everything short of releasing the rocket. So significant development, really signifying significant progress. Our last major milestone on the path to launch. So big accomplishment.
Yeah, and you mentioned the development. Designing, building, testing a new rocket comes with a whole bunch of challenges. Can you talk a little more about the Vulcan team and what it took to get to this point?
Sure. Well, when we talk about the Vulcan team, it's really the whole ULA team contributed to this. We may have started out many years ago with a small team, but this is our future. This is a ULA product, and everyone at ULA has played a significant role of this, and this is the future, and this is what we'll all work on down the road. A significant accomplishment that when we started out, we had a group of folks that had extensive experience, building and launching rockets and designing missions and integrating payloads. And one of the keys to the success of Vulcan was taking all that experience and really using that to develop a next generation rocket. And that's what we've done with Vulcan, and it's going to serve us very well.
Can you talk about what this test really meant to you personally? I know you and the whole ULA team have worked really, really hard to get here.
Well, yeah, like we said, it's one of the last significant milestones on the path to launch, so it's tremendously gratifying. It's one of those things, until you actually see it, it's hard to actually envision. You're sitting there, you've looked at that hardware in some cases for years, stationary, and while it wasn't lifting off, to see it actually functioning with the engines firing and all the systems working together is just, as I said, it's terribly exciting, very gratifying.
Absolutely. Well, again, congratulations on getting to this monumental day, and thank you so much for joining us.
Thank you.
This is Vulcan Mission Control. I'd like to congratulate the entire ULA team on getting us to this historic day. Stay updated on Vulcan next steps by following our live blog at ulalaunch.com. I'm Amanda Sterling, and thank you for joining us. Before we sign off, we'll take another look at our successful flight readiness firing, which occurred at 9:05 p.m. Eastern Time. 8, 7, 6, 5, 4, 3, 2, we have ignition.
LC switch not ready. Countdown clock to
We
T-minus
just
7
saw
minutes and holding.
ULA's Vulcan engines throttle up for the first time.